Michelle.
The larger amount of time to live it, like the larger the trial, the more you closer.
Because it's a what?
Because you have like a 50% chance of getting your stuff and then
Yeah. So as we do more trials, flip the coin more times, we would expect that the proportion or percentage of heads goes to 50% because flipping a coin is a 50-50 chance. You have 50% chance of heads, 50% chance of tails. So today we're going to define probability, talk about the law of large numbers, the law of averages, do some simulations. We got a lot going on today. And don't make me take my coins back early. They can sit nicely. No flipping. They're in the middle. All right. So the fact that the proportion of heads in many tosses eventually goes to 0.5, which is just the decimal equivalent of 50%, is guaranteed by the law of large numbers. This law states that if we observe more and more repetitions of any chance process, the proportion of times a specific outcome occurs approaches a single value. The probability of any outcome of a chance process is a number between 0 and 1. We use decimals. Sometimes we'll use percentages, but percentages can always be turned into decimals, so they're still meeting that criteria of living between 0 and 1. And they describe the proportion of times the outcome would occur in a very long series of repetitions. Outcomes that will never ever occur have a probability of 0. Never ever occur. And outcomes that will always occur have a probability of 1. Down below, I have some sample questions of what you'll see in your homework tonight. So over here it says, according to the according to the Book of Odds, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. Explain what a probability of 0.61 means in this setting. So we're not getting away from interpreting things in context. We still have to do that. So, down? Good? So when you're asked to explain a probability, the key phrase you need to have is that in the long run or in a long series of repetitions. So I have to write small. I should have given myself more space. In the long run, we would expect the proportion, I'm going to abbreviate proportion so I don't run out of room. U.S. adults. Say that again? I know, I'm sorry. Who eat breakfast is 0.61. Really, honestly, all I did was I added in the long run and then put we would expect the proportion of U.S. adults who usually eat breakfast is 0.61. Noah?
If you interpret it on a test, would it be still right if you put 61%?
Yes, that would be fine. Part B of that question says, why doesn't this probability say that if 100 U.S. adults are chosen at random, exactly 61 of them eat breakfast? So choosing 100 U.S. adults is not considered a long series of repetitions. It's a small, you're looking at what's happening in the short run instead of the long run. Probability is all about what happens in a long series of repetitions, which we use long run interchangeably with that idea. So if we're only looking at 100 U.S. adults, that's a short run or a small sample size. And so we can't say that it's going to be exactly 1. We can't say for sure what's going to happen in the short run. On the right, it says probability is a measure of how likely an outcome is to occur. Match one of the probabilities that follow with each statement. And I'm going to have you guys try this one on your own. Remember, a probability of 0 is something that will never ever occur. Probability of 1 is something that will always occur. So there are 6 probabilities listed. There are 4 situations, so you may not use them all. Go ahead and match the situation with what you think the correct probability is. I used to, before COVID, have desks in groups, and so I could really grow, and now I feel really trapped when I walk in on that. All right, who would like to share which probability they put for A, the outcome is impossible, it can never occur? 0. I saw some of you put A under the probability too. B, the outcome is certain, it will occur on every trial.
1.
1. C, the outcome is very unlikely but will occur once in a while in a long sequence of trials. 0.01. And then D, the outcome will occur more often than not. 0.6 or 0.99. Both of these occur more often than not, right? So 0.3 doesn't occur more often than not because its complement would be 0.7. So for D, you could have done either one of these. All right, and then down below, we're going to talk about the law of averages. Anna's a softball player. Do I have any baseball players? What? Cheyenne, you play softball. You guys have heard of the law of averages, right? Baseball and softball, always, I bring up the law of averages, and they will argue with me that it is so real, and it's not. So, a few years ago, an advice columnist published a letter from a distraught mother of 8 children. It seems that she and her husband had planned to limit their family to 4 children. When all 4 were girls, they tried again and again and again. After 7 straight girls, even her doctor assured her the law of averages is in our favor 100 to 1. Is it true that since in the long run the probability of having a boy is 0.5, that the woman and her husband are more likely to have a boy for their 8th child? Nate says, Michelle?
It's 50-50 each child.
Sorry, speak louder.
Isn't it 50-50 each child?
It's 50-50 each child. So it's not more likely that they have a boy because they've had 7 girls in a row. The law of averages is this myth that they say out there, and baseball and softball tend to, say, oh, this, I don't know a whole lot about baseball and softball, so I'm going to throw out a number and it's probably not right. So they'll say that the guy up to bat has a batting average of like 0.4, and he's struck out the last 3 times, and the announcers will be, oh, the law of averages says he's got to get a hit this time. And it's not true at all. But that's the most common place you hear about the law of averages is baseball and softball. And I feel like if Trey was here, he would argue with me.
Even if you were right
Yeah.
here.
Another thing, remember probability is in the long run. So if we looked at a really large sample size of babies, we would expect half and half for boy and girl. 8 kids is what would be considered the short run, so we can't guarantee that this woman and her husband should have 4 boys and 4 girls out of 8 children. That is a lot of children.
Yeah. You're working 8 times.
When I was in high school, I thought I wanted to have 6 kids.
Oh my god.
I don't know.
After your first child, you're like, why would I?
Yeah. After my first, I was like, no, not gonna happen. All right, can I flip? All right. Shaquille O'Neal is a 50% free throw shooter. Actually,
No.
it is a cap, I'll be honest. I'm pretty sure he's worse than 50%. But for the sake of nice numbers, we're going to say he's a 50% free throw shooter. 1 week he shot 50 free throws. In one of the games he made 6 free throws in a row. Is this a hot streak or did it occur purely by chance? Purely by luck. Yes, purely by chance. Which, by the way, is going to become a phrase we use throughout the rest of the year. And you guys probably know by now I am really lazy and I'm not going to write it all year. So when I say purely by chance, I'm going to put PBC. And just know that that's what I mean. PBC. Which is more likely to happen when tossing a coin 6 times? Heads, tails, heads, tails, tails, heads, or tails, 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 heads, heads, heads. Nobody wants to give a thought.
The first one.
Sam and Zach say the first one. Anybody vote for this one? I never should have put you that far away from me. I can't hear you.
I just want to talk, it's fine.
Nate?
Aren't they equally likely?
They are equally likely.
Good job.
That's what I was thinking.
Each toss of the coin has the same chance, 50%, of being heads or tails. So you have the same chance of getting heads, tails, heads, tails, tails, heads as you do as getting 3 tails and 3 heads. True or false? Mr. Wilcox's brother-in-law has 3 girls. His next baby is more likely to be a boy because... All right, false. That is false. We still have a 50-50 shot of boy or girl. Any questions before I move it up? All right, so probability models. A sample space. You need to know that term. It's why I bolded it. If you see in your homework, draw the sample space, or I think it usually says draw. It might say write out the sample space, or it might tell you to write S or draw S. S means sample space. And sample space just means that we list all the possible outcomes for that situation. So some sample spaces are really simple, like flipping a coin. What are all the possible outcomes of flipping a coin?
Where's my seat? I thought I sat there.
Yeah, but I moved everybody.
Oh, my bad. Wait, will I get marked as tardy or absent today?
Are you tardy or are you...
I'd say I'm tardy. I do a little rounding.
Where were you?
Oh, I was getting a haircut. That's why I'm wearing a hat. I don't like what she did to my shit. I mean, it's
You
not
still have
bad.
to pay
It'll,
her?
I'll grow into it.
And you still have to pay her.
I still have what?
To pay her.
Yeah.
That sucks.
Well, what am I to do? She's running a business. I can't just run out of there.
True.
So I'm only tardy?
Sure.
I see.
You're not directly behind Bailey, but one behind. Thank you. I don't, one empty desk and then you. All right. What are all the possible outcomes for flipping a coin? Heads or tails? So you put an S to say it's the sample space. Then you put an equal sign, and then you use those fancy little bracket thingies. Like that. Good. They're not like a parenthesis. They,
Backwards 3.
well, no,
Braces?
is that what they're called?
Oh.
Yeah,
Why can't we just start
because that's not how,
It's just not how.
no. Heads is one outcome, comma, tails is the other. I'm really good at making the brace on that side, and then my other one, I can't. All right, so what would be the sample space if we roll 2 dice and record their sum? What are all the possible sums of 2 dice? 12 is one of them. What else? 2 through 12, right? Double aces is the smallest, and that'd be 2 when you add them together. 6 and 6 would be the biggest sum, and 6 plus 6 is 12. 2, 3, 4, 5, 6. What?
Just make like backwards.
I suppose.
Not just use an
Oh, what?
List all possible outcomes.
That's what n-dash does.
No. You're not going to like what we do in a minute, Nate. Yes.
What is, like, how would you explain the,
Yeah.
You tell them.
this
Period.
Explain the sample space is heads and tails. Well, we're rolling 2 dice,
Oh, right.
and then we're adding the numbers. Then the third one, we're going to roll a die and flip a coin. I never should have given coins out.
I don't even know what
What are you doing, Calvin?
30 dice.
We're going to do dice in a minute, okay?
Oh, awesome.
All right. What would be a possible outcome of rolling a die and then flipping a coin? What could you get?
3 heads.
3 heads. What else?
3 tails.
3 tails.
Oh, you can do
So I
every
could-
number for every coin.
So I could get 1 heads, 1 tail, 2 heads, 2 tail, 3 heads,
Oh my god, that's it.
3 tail. What are you confused about, Hannah?
I don't understand how to get 2 tails if you only have 1 coin.
Roll a die, flip a coin.
Yeah, you only flip it once.
Yeah, it's.
Right, that's the
it's
number
like
I get on the die.
Oh.
And then that's what I get on the coin.
Why did that?
Wait, oh my gosh,
I'm going to run out of room. Hey, Hayden,
Yeah, just put infinite.
Yes.
can you turn your music down, please?
you can hear it. How can you hear that? It is real loud.
Yeah. Am I just deaf?
Thank you. All right. I ran out of room. Sorry.
Are we going up to 6?
All right. Now we're going to write out the sample space for rolling 2 dice.
We are going up to 12 or 6.
Sorry, Nate.
No, 26.
Oh, goodness. So, this one obviously is pretty big, right? That's why I left a lot of space, although I should have given myself more space there. So, sometimes you might want to make big braces. Oh, and it's not that bad. So, I'm rolling 2 dice. So, I could get a 1 and a 1, right?
Correct.
I could get a 1 and a 2. I could get a 1 and a 3. 1 and a 4. 1 and a 5. 1 and a 6.
Oh my god.
Oh my gosh, it's not that bad.
Okay.
2 and a 1. 2 and a 2. I'm going to stop saying them out loud at this point. So sometimes your sample space is really simple, like flipping a coin. Sometimes it's a little more complicated, like rolling 2 dice.
Find a way to cheat the system.
Find a way to cheat the system, is that what you said?
Yeah.
I will say that one of the ways to help you get the correct probability sometimes is writing out the sample space. Because then you have more of a tangible for figuring out how many ways you can get what you want out of whatever you need. Like if I asked you to find the probability that you get a sum of 7 when you roll 2 dice, it's really easy to see that there's 1, 2, 3, 4, 5, 6 ways to get a sum of 7, and there's 6 times 6, 36 outcomes. So sample spaces, even though you think they're tedious, sometimes they're nice. Can I flip my paper over? I like that. Why not? So another definition, that's why the word is bolded. An event is an outcome or set of outcomes an event must be a subset of the entire sample space. So an example of using that definition, a coin is tossed 3 times. We're going to list the outcomes in the event A of getting exactly 1 tail. So just to make you guys love me that much more, we're going to do our sample space. So we're tossing a coin 3 times. Does anybody know how many possible outcomes there is for tossing a coin 3 times?
3. 2.
I could get heads, right? And then I could get 2 heads and a tail. Or I could get a heads, tail, heads. No, it's not.
Nah.
Or I could get tail, heads, heads. Right?
10, 10, 10.
I could get a tail, tail, tail. I could get a tail, tail, heads. Or I could get a tail, head, tail. Or I could get a head, tail, tail. Right? See why listing your sample space is important? Because you guys were just guessing. 6, 3, 27. There's 8 possible outcomes for flipping a coin 3 times. Event A is that we get exactly 1 tail. So A means we could have heads, heads, tail, or heads, tail, heads, or tail, heads, heads. Those are the 3 ways that we could get exactly 1 tail. So then if I asked you, what's the probability of event A? We would know there's 3 ways to get A, and there's 8 total outcomes. which would then, I could turn it into a decimal, which would be 0.375. Or if you're more of a percentage person, 37.5%.
Can you say that whole thing again?
Yeah.
For A.
Probability of A. That's how problems will be written. Sometimes they'll be written in words, sometimes they'll be written like this. So if you have P, and then whatever's in the parentheses, that tells you the event. So the probability of event A happening. Event A was that we got exactly one tail. So we had those 3 ways to get exactly one tail. There are 8 possible outcomes. So the probability that event A happens is 3 out of 8, or 0.375. Questions? You guys are going to try this one. Hold up. The sample space we already did together. This big one down here. Okay? So all you need to do is list all the outcomes for A that you get a sum of 7. So you need to give me the different ways you can get a sum of 7 when you roll 2 dice. And then I want you to tell me what the probability of A is, please.
There's like a pattern. There's no idea. Oh.
They all add up to 7.
Oh. See, I thought that was just dumb.
That's the only math I can do.
We already have our sample space on the previous page. Because we're taking a die and tossing it to the time. Oh, I'm sorry. Don't go to the back. You go put it on the board. You need your paper to do it.
I think I do need it. Hold on. Wait.
I can use those.
So here's the sample space for causing 2 dice. You can get a 1 and a 1 and a 1 and a 2. Well, we're not doing the sum. The sample space is for just tossing a die twice. No. Dice only goes up to 6.
Wait, so should I put
Alright, so if you go back, here's our sample space for rolling 2 dice or rolling a die twice. So here I said rolling 2 dice. Here I said rolling a die twice. It's the same sample space. We wanted to find all the possible ways we could get a sum of 7, which is the diagonal here. And there were 6 ways that it could be done. And there are 6 columns and 6 rows. I always mix columns and rows up. 36 outcomes. So she listed the 6 ways we could get a sum of 7, and then she did 6 out of the 36 total outcomes, which gives us 0.166 for our probability of it. Any questions?
Do we have to change it to 16.6%?
No. Most of the time our answers will be decimals. Every once in a while, a percent will be in there, so I just wanted to remind you that you can convert them back and forth. All right, so the probability, which I already introduced this notation, probability of A, of an event satisfies this statement. Our probability of A has to live between 0 and 1. We already talked about that. All probabilities have to be between 0 and 1. So if I ask you what's a mistake in a statement about a probability and it's less than 0 or greater than 1, that's the mistake. The other thing, trying to think of how to word this. If you're given a sample space and you're told all the probabilities, they should add to 1. So let's say, I'm trying to think of a quick example. Think of one. Sorry, Maddie, it's not you. I'm just staring. Let's go with this. If I were to have 5 numbers, 1, 2, 3, 4, and 5, and I were to write each one on a piece of paper, crumple them up, and put them in a hat, they all have 0.2 probability of being the one I pick out, right? Because there's 5 of them, and I'm picking 1. 1 divided by 5 is 0.2. So sometimes you'll be given the outcome and the probability, and they'll ask you which one is the correct probability model. You have to check that the probabilities add to 1. They can't add to anything but 1 for it to be a correct probability model. They can't add to 0.98, then you're missing 0.02. So they always have to add 1. The numbers, I came up with an example. I said if I were to put the numbers 1 through 5 on a piece of paper and pick one, they all have 0.2 probability of occurring. Now, I have this in math terms right here. But for whatever reason, I've noticed in years past that that statement isn't enough for kids to remember that all probabilities must add 1. So if S is the sample space in a probability model, then the probability of S is 1. Because if I were to have all the outcomes from my sample space happen, like up here, if all of those ways to toss a coin 3 times happened, I'd have 8 out of 8, 1. So that statement tells us that when I add all the probabilities in my sample space, they have to add 1. But like I said, I've noticed that doesn't always click. So hopefully adding that part does. We have our first probability rule. It's known as the complement rule. I want to say we have 8 rules. And no, you won't get them on a sheet or anything. You have to have them memorized. I'm sorry. I know. I just ruined your day. All right. The complement of any event A is the event that A does not occur. We write it as A with a little c in the exponent position. So I'm going to go back up to my examples up here. So this bottom one, not the coin toss, the die rolling. Okay? So the probability of A, Jillian came up here and showed us, was 6 out of 36, or 0.166. That was the probability that our 2 dice added together made 7. So the complement rule tells us that the probability of A complement, or A not happening, is 1 minus the probability that A did happen. So if we were rolling a die twice, and we wanted to find the probability that when we add the numbers together, we get something other than 7, or the sum does not equal 7. Up here, we found the probability the sum did equal 7. So I could define this as the probability of A complement. And then it'd be really easy for me to go, okay, well, I'm going to take 1 minus the probability that A did happen, which Jillian showed us was 0.166. So I'm going to do 1 minus 0.166, which is going to give me 0.833. I think actually 834. 834. I'm thinking. I stare off into space when I'm thinking. I wasn't actually asking. Questions on our complement rule? Complement. Yeah, you have a question. What is
A lot
it?
of questions.
Ask them.
I don't even know what that is. That'll be that.
Okay, so up here, we found the probability that when we rolled 2 dice and added the numbers together, we got 7, correct? And you were good with it being 6 out of 36, or 0.166. Here, I'm going to say, what's the probability that we roll our dice twice, and when we add the numbers together, our sum is not equal to 7?
Wouldn't this be 30?
30 out of 36, which is what? 0.8333.
So what's the whole 1 minus p?
Because sometimes it's not as simple. You don't know the sample space and know that there are 30 other options. You just know that the probability A happens is this. So the probability A doesn't happen, or A complement, is 1 minus the probability that A happened. Did that clarify? Anna?
So like, what does this, you probably just explained it, but I was confused. What does this like tell you? Like the percentage of it not being in the whole probability, like out of all the numbers?
So if I were to, I think I'm going to answer your question, but let me know if I don't. So there were 36 outcomes, right? So if I were to find the probability of each outcome, that'd be 1 out of 36, which I don't know the decimal off the top of my head. But so if I add all the probabilities together, I get 1. So the probability that my sum is 7 is 0.166. So the probability that my sum is not 7, or the complement
Oh,
of this event, would just be 1 minus that probability.
okay. I get it.
Any other questions? I like questions. I want to make sure we get this. Like I said, probability seems like an intuitive thing, but it often is not.
So the probability that the sum isn't 7 is 1?
Is 1 minus the probability.
Oh.
I guess it might help if I say 1 minus the probability the sum is 7, which we defined the sum being equal to 7 as event A. And we know event A had that probability. So I took away. Good. All right. I always go back and forth with this example. I like it. We're gonna do it. Oh, don't give me that. It's not bad. The thing is, one of the best ways to determine probabilities is through simulations, which is why I have simulation up there. But we honestly don't do it a whole lot in this unit. So then I go back and forth. Should I do it? But I do. I need to do it. Yes, I need to do it. Don't tell me no. All right. So Mountain Dew is doing a special promotion in which they are giving away free prizes. Mountain Dew claims that under the caps of 1 in 6 bottles, there is a prize awarded. Mr. Wilcox purchased an 8-pack of Mountain Dews. None of them were winners. He thinks that Mountain Dew is lying about their claim. So the imitation of chance behavior based on a model that accurately reflects this situation is called a simulation. Now, in your book, you guys have noticed that sometimes in the instructions, it'll tell you to follow the 4-step process. And I have told you, you don't have to worry about that because I never felt it really helped. Well, now I feel like it does help. The 4-step process is state, plan, do, conclude. Remember back before COVID when we gave you work samples in math class? And you would restate what the question is asking? And then you would come up with a way to solve the problem, and you would do it, and you would explain what it meant, right? That's really what state, plan, do, conclude means. We're going to state what the question is asking. We're going to come up with a plan for answering the question. We're going to do our plan, and then based on our math, we're going to make a conclusion. So, state, what we want to figure out is what's the probability that we buy 8 Mountain Dews. Where did it say? He bought an 8-pack. Mountain Dew claims 1 in 6 is a winner. So what's the probability that we buy 8 Mountain Dews and none of them win when Mountain Dew says 1 in 6 is a winner? Now, as I said before, I'm lazy, and what's the probability is going to be a lead-in for a lot of questions this unit. So if you see me write WTP, that means what's the probability? And I'm going to abbreviate mountain. Excuse me. So I put this under simulation. And I defined simulation as the imitation of a chance behavior. So we want to imitate that 1 in 6 are winners. What's a chance behavior that has 6 outcomes? Dice. Rolling a dice, right? So that's going to be our simulation here. We're going to roll dice. Let's see, I'm going to use a different color. So our plan is to simulate 1 in 6 being winners. By rolling dice. Or I should say die. You guys are going to get used to me not saying die pretty quick. I know die is singular and dice is plural, but I often use them interchangeably. So, before we roll our die, we need to decide what number means we win and what other numbers mean we lose. So Mountain Dew says 1 in 6 is a winner. So on a die, there's 1, 2, 3, 4, 5, and 6. Which number, anybody, do you want to be the winning number? 7? Who said 7? No 7s. I'm going with Cheyenne because I saw her hand first. It was 3, right? So we're going to say a 3 means we win. 1, 2, 4, 5, 6 mean we lose. Now, the question we want to answer is that we buy 8 Mountain Dews and none of them are winners. So we need to define we're going to roll the die 8 times so that we represent our 8 Mountain Dews. So I'm going to say 1 repetition. Repetition is 8 rolls because we bought an 8-pack. Now, we would like to do as many repetitions as possible, but sometimes when you're doing a simulation, you can't do a huge number of repetitions. But remember, probability is always better in the long series of repetitions. So for this, because, well, we're running out of time, we're going to do 5 repetitions. I'm trying to think. Usually I have you guys roll the die too, but I don't know if I have enough time to hand out dice and have you roll them.
You should just do it so
You just want to watch me roll dice?
Yeah.
Okay. Die. Here's my die. Okay. So I'm going to do 5 repetitions. Because like I said, we want to have a long series of repetitions, but when we do the simulations, sometimes we can't do a huge amount of repetitions. Your calculators will simulate rolling dice for you, by the way. I'm going to do 1, 2, 3, 4, 5. So there's my 5 repetitions. 3, or 1 right away. 4, 6, 4, 1, 6, 5, 1. So that's 8, right? So then I'm working on my second repetition. I get 1, 2, 6, 6, 1, 3, 2, 4. 2, 4, 5, 5, 6, 5, 2, and 2. Repetition 4, 4, 6, 6, 2, 5, 1, 4, 2. And then my last repetition 2, 4, 4, 4, 3, 1, 1, 2. All right, so our question was, what's the probability that we buy 8 Mountain Dews and none are winners when Mountain Dew claims 1 in 6 are? So out of my simulations, I had a winner in my repetition number 1. I had a winner in repetition 2. Repetition 3 had no winners. Repetition 4 had no winners. Repetition 5 had a winner. So when you do a simulation and you're writing your conclusion, you have to say based on my simulation, because my conclusion is only based on what I did. I can't say it's what's going to happen every time. We would expect an 8-pack to have no winners. I had 2 of my repetitions out of 5 have no winners. 2 out of 5 is 40%. 40% of the time. So the fact that Mr. Wilcox went and bought an 8-pack and had no winners really isn't that unusual. Based on my simulation, that's going to happen 40% of the time. Questions? In your homework, if you see questions that ask you about whether simulation designs are valid, go ahead and try them, but I will talk about that at the beginning of class next time. But go ahead and try them, okay? Yeah?
How is it 40% get no winners?
I had 5 repetitions. Repetition 1 had a winner. Repetition 2 had a winner. 3 did not. 4 did not. 5 had a winner. So out of my 5 repetitions, 2 of them didn't have a winner. So 2 out of 5 is 40%.
I thought we were counting like all of them.
Oh, yeah, that's true, because I did do 40 rolls total.